Hello everyone and welcome back to Educator.com. I'm Dan Fullerton, and in this lesson we're going to talk about electric potentials due to continuous charge distributions. Our objectives include calculating the electric potential on the axis of uniformly charged disk and deriving expressions for electric potential as a function of position for some uniformly charged wires, some parallel charged plates, coax cylinders, and some concentric spheres. So let's dive right in and let's start looking at the potential due to a charged ring. Find the electric potential on the axis of a uniformly charged ring of radius r and total charge q at point P located at distance z from the center of the ring. So first, let's draw a picture of the situation, and we've done this before for electric field, but it's going to look kind of like this. There are axes, we'll call this our z, this will be our y, that can be our x, and we'll put our ring on it like that, and we're going to look for the potential at some point P over there. Well, the first thing I'm going to do again is break this up into some little portions where we've got some delta Q over here, and we'll find the distance from delta Q to that point P. There we go. And we'll call that Ri. Now that we've done that, let's also mention that this radius is capital R. So to find the potential at point P, that's going to be the sum over all these little itty-bitty pieces of their potentials, which is 1 over 4 pi epsilon naught times the sum over all I of the charge contained in that little bitty piece, Qi, divided by Ri. Which implies then that the potential at point P is going to be 1 over 4 pi epsilon naught, and as we make all of these little bitty pieces smaller and smaller and add them up, we can integrate. Charge is going to be that little bit of charge, dq, divided by r. But in this case, our r as we go around this circle is going to be the same. It's constant everywhere. Ri is equal to r. So, since we know that Ri equals r, we can say that the potential at point P is equal to 1 over 4 pi epsilon naught. This is a constant. It can come out, and we can even replace it with Ri, integral of dq. Well, our integration just got pretty easy. If we go all the way around the circle, adding up all the little bits of dq, well, the integral of dq, the integral of d, that's a little q, is just our total charge, capital Q. And we also can tell Ri pretty easily using the Pythagorean theorem that Ri is going to be the square root of z squared plus capital R squared. Therefore, our potential at point P is going to be Q over 4 pi epsilon naught times 1 over square root z squared plus r squared, or Ri. Pretty straightforward derivation for the potential due to that charged ring.